let's see. So hopefully everyone's ready. So, class. Wow, I got one. Almost a 2 over here. I'll wait. I'll wait for you. Come on, let's try this again. So, class.
Yes.
Thank you. All right. At least pretend like you want to be here, because you know what? Why not?
You got back to basics.
I know, right? So, think of it like this. You have 9 weeks left of school, period. That's it. Just 9 weeks. 9 weeks left. And in this course, we finish math early. Because of all the testing schedules, we finish the beginning of May. Because the AP test is actually supposed to be like May 2nd or 3rd or something like that. It's beginning.
I thought it was on a Monday somewhere.
Yeah, it's in May though. So it's actually like one of the first weeks in May. So that means you finish this class that much earlier, which is almost 3 weeks early. So that means we actually have to finish our curriculum before that. So we could start doing test prep and all kinds of stuff. So we just need to finish up our calculus stuff, and then we could start working on trying to do test prep to actually improve our understanding. So for me, I'm asking that get everything caught up and done. So the deadline was last Friday, right? For everything? Okay, did you guys all get that in or no? Did it not happen? Yeah, everyone is down with the sickness. So I'll still take it. If you want to come in after school and get some help, I could dedicate a Monday after school. I don't have games those days. I don't have practice set up for those days. But if you guys want to come in, I'll sit here next to you and actually help you do your math on Mondays. Okay? Because our schedule for games is actually Tuesday, Wednesday, Thursday. And sometimes we have matches on Friday too, so I can't commit to that. But I will commit to Mondays. If you want to come in, sit down, take time off work, maybe if it's just 30 minutes. If that's all you need, great. But I will be here for that, okay? All right, fundamental theory of calculus. So what we're actually doing here, this is the big idea. And so when you're looking at calculus problems, they'll actually just refer to it as FTC 1. So part 1 or FTC 2. Part 2 of the fundamental theory of calculus, and interpret integral rates of change, all that. So it's abbreviated. It's kind of annoying, but it is. Let the function that is continuous on a closed interval from a to b, the function I, be defined by the I of x, where we are doing our bounds from our lower bound of a to the upper bound of x, we get of f of t to dt. So that means that in this function, we're integrating 4 x's, so I'm changing out the t's for my x's. The property is continuous on the interval and differentiable on the interval from a to b, which is not included. This is actually a open, and this one is closed, okay, for all x within those values. So what it means is, if I take the derivative of the integral, I'm going to get just the function. So, if you remember correctly, when I take the derivative of something, and then I take the antiderivative, that's going to put me back to the original problem. Right?
Yeah.
That's what this is actually telling you. So, as we go through, if you take the derivative of the integral, we get the function. Okay? Or vice versa. So if I have the integral and I take a derivative, that would give me the function. But both works either way. So depending on which function we're looking at. Okay, so for this first one right here, I'm actually showing you how it's going to work out, and that's why it is looking like this right here. So for this first part, I'm going to actually have the bounds from 0 to x. So let's go ahead and look. So if I'm going to take the derivative, so I'm going to take this right here, and I'm going to move it to another page so we can see this. From 0 to x, hopefully I wrote that correctly. Yep. All right, so we're going to do this in two separate parts. So first, let's start with the integration part. So starting with the integration, so from 0 to x, so I'm going to do dx here in a minute. 0 to x, remember when we take the integral of this, I would actually have to start plugging in what I have. So this is going to undo what we already have. So from and that's going to be dt. There we go. Break it down. And then we have to take it from my, again, 0 to x. Now, let's look at chain rule. If I were to take the derivative of this, wouldn't that be the chain rule?
Yes.
Yes, that would be a chain rule, right? Derivative of the inside. So let's look at that piece first. So I'm going to have, and that's going to be, my u is t plus 1. My du is going to be 1t, right? Just 1. That's a du. That's a horrible u. And this is going to turn into the u to the 1/2.
Okay.
And now take the derivative. Take the derivative of that. It's going to be 1/2 u to the negative 1/2 times the derivative, which is 1. And now plug it back in. So I get 1/2, and then I get t plus 1 to negative 1/2. So the integration undoes the derivative. Ugh. I'm not feeling well. Ugh. It was 46 degrees when I left my house.
Oh yeah, it was getting colder as it's summer.
I know, right?
Yay.
I had hail on my
Really?
house yesterday. Yeah.
Oh my
I was like, what the hail? See what I did there? See what I did there? What the hail?
Great weather. Great weather.
And I was like, hail yeah.
It's better than the road being very hot and burning your tires
Okay.
off.
Anyway. All right, so let's go ahead and take the integration of this. So the integration is the opposite of the derivative. It will undo it. So that means that I'm now going to take integration Now, do you know what's the antiderivative of that? It's not a trick question.
Oh yeah, it goes back to the original.
Yes, it goes back to the original, right? It's going to give me this, right?
Yeah.
Okay, so taking the derivative and then antiderivative or integration of that, it should go back to that. So, but this time, it's now gonna look like this. It's now gonna be t plus 1 from 0 to x.
Is that meant to be a straight line?
That is a straight line.
Okay.
So that's, we took the integration and that's my bounds. So it's a straight line up and down, so it's our bounds, our lower bound and our upper bound. Which would turn into, it's gonna be, plug that in for my, I get x plus 1. Okay, there's my upper bound, minus my lower bound, which is gonna be 0 plus 1. And so from here, we are now going to come up with, it is square root of x plus 1 minus 1. But now this thing over here is referred to as the constant. There's some constant that is going to be there all the time. Whenever I have a integration, there is some constant I add. Because when I take the derivative, 2x plus 1, if I take the derivative of that, it would be 2, right? And so this is my constant that I lost when I took my derivative. And so if I took my integration of this now, if I took the integration of this, I would be plus c, plus some value, some constant that we're going to have over there. And that's where that comes from. So there's going to be some constant. So that is going to be referring to this thing over here at the end, which is the minus 1 is my constant that was there. I'm out of breath already. All right, kind of makes sense or no? So in my thing right here, this is my plus c that I have there. Because after I have that, I will have some constant. I take the derivative of that. Now, let's go ahead and look at the other one. So from 2 to x. S cubed minus 1. 2s squared plus s plus 1. All right. So what rule is this going to be here?
Quotient.
That is going to be a quotient rule. So let me see. Can I do some factoring, maybe? To maybe try to make this a little bit easier?
You could try and factor out the denominator.
Okay, if I factor out the denominator, what would that be? Do you guys remember the AC method? Or kinda? A,
Yeah.
B, C. So 2 times 1 is 2. And so they have to equal 1. Right?
Yeah.
They have to equal 1, positive 1. So could that be like a positive 2 and a negative 1? Say no.
No.
Why?
They all need to be positive.
It's got to be positive, right? So that's not going to factor. What about the top?
Equal
with the top factor?
Take out an S.
Nope.
Or you can do that. What's that rule? It's like the square rule, except it's the other one.
Yeah.
I forgot its name now.
Denny? Can we factor the top? What's this? What's another name for this thing right here?
Difference of a cube, or is it?
Difference of cubes.
Okay.
So 1 is a perfect cube. And s cubed is also a perfect cube. So that would turn into s minus 1 times s squared plus, let me see, that's going to be, that times that, so it should be just s plus 1. So, it doesn't look like it would factor either way, right? Because there's that 2 there also. If it was s squared plus 2 s plus 1,
Wait, what are we?
actually it is that.
What do you
Nope, it's not. Yeah, you're right.
Okay.
Because that one right there would be s plus 1, s plus 1. That's what that one would be. That one's the perfect square.
Oh, perfect.
So it's this squared would give me this. So, but this one right here doesn't factor. This piece right here is prime.
Okay, so.
Am I a little bit too much algebra first thing after spring break?
Well, I was like, you could factor the denominator with that idea.
Oh, watch. Okay, let's distribute s cubed plus s squared plus s right here minus s squared minus s minus 1. S cubed 0, 0, minus 1.
Okay.
So that's where we get the difference of cubes there.
You said perfect square is s squared plus s plus 1. Okay. I'm like, we could somehow get rid of that 2 because perfect square right there. But it's not perfect square.
So if it was a square like this, there would be a 2 in the middle.
Oh, yeah.
That's where the 2's at. Whole lot going on.
Too much factoring early. Too early to factor.
Okay. All right. So are you copying it down or should I wait?
I copied the.
Okay.
Yeah.
So either way, I'm showing that it's not going to be factorable. It's not going to be able to cancel out most of what I have. So I'm just showing that that is not going to. So that's the one thing I want to try and do before I do a complicated problem. Okay. All right. So I'm going to erase what I have here and start with my fundamental theory. So we're going to undo this. So let's start by taking my derivative.
Okay.
Let's take the derivative. So that's going to be a quotient rule, right?
Yes.
So if it's f, f is, let's do f prime would be 3s squared. G prime is going to be 4s plus 1. You ready? Okay, so right here, I'm going to go ahead and do my quotient rule. So it's f prime g, so it's 3s squared, f prime g times 2s squared plus s plus 1 minus g prime, which is 4s plus 1, g prime f, which is s cubed minus 1, all over g squared. Yes? Okay, so antiderivative. So I'm not going to clean it up, but antiderivative is going to undo that, right? So if the antiderivative undoes that, then I'm going to be left with the original, which is up here. So it's going to be s cubed minus 1 to s squared plus s plus 1, and that's from 2 to x. And now we're going to plug that in and evaluate the top and bottom. Minus the bottom, the lower bound, which is going to be 2 cubed minus 1 over 2 times 2 squared plus 2 plus 1. Now all this right here is some number, right? Is there any variables left in there?
There's no
No,
variables.
there's no variable. So if it's not a variable, then it is a
Constant.
It's a constant. That's going to be my plus c value. So it's my plus c, what we get over there. So all of that becomes my c value that I'm eventually going to have from taking that. So when we go back to the problem, it's just this. Because my lower bound is just going to become my plus c, because all my variable goes away. Does that make sense? Kinda. Hopefully. On occasion. No. Let's see where we're at now. You want to do one more, then we will work on homework? It's 19, so that's 30. Yeah.
Alright.
One more, then we'll work on homework. Now, I'm going to skip some steps on this one. Do we have to take the derivative
No.
and then take the antiderivative? No. what is it saying that we're gonna do? When I undo it, I'm just gonna have to evaluate it, right?
Yeah.
So I take the derivative and then I undo it to get my integral, then I just evaluate for my integral. So it's now gonna be e to the t plus t from 4 to the 3x squared plus 1. Try and evaluate it, please. So every place you see that t, you're replacing it with that whole quantity. Now, all of this right here, all of this, e to the 4th, that's a number, isn't it? It's not a variable, is it? E is a number,
Yeah.
4 is a number. So all this right here is going to become some constant, right? And so my answer is going to be here. All right, so I know you guys worked really hard on 5.2. So if you didn't, you're gonna finish it today, and tomorrow's the I-Day. It is gonna be due tomorrow. Make sure you all like, share, and subscribe.